Welcome to The Explainer. Today, we're diving into something totally transformative. We're going to look at how ordinary, parked electric vehicles can literally be turned into highly profitable mobile power plants. If you're curious about the future of the energy grid and electric fleets, you are absolutely in the right place. Let's get right into it.
Okay, I want to kick things off by hitting you with a number that completely changes how we think about electric vehicles. 96%. Just let that sink in for a second. Research shows that EVs spend up to 96% of their entire lifetime parked and totally unutilized. They're just sitting there, right? Collecting dust. When we look at that sheer inefficiency, a huge question pops up. How can we unlock this massive untapped potential? I mean, we've got all these powerful lithium-ion batteries just chilling in our driveways and office parking lots.
Section 1. Front and behind the meter. So, to actually extract value from a parked car, we've got to understand the energy mechanics. When an EV plugs into a building, its battery can theoretically interact with two completely different worlds. On one side, we have behind the meter, or BTM. These are consumer-oriented applications aimed at maximizing economic results for the building owner. You know, like managing the building's own power load. On the flip side, we have in front of the meter, or FCM. These are grid-oriented services that actually help stabilize the wider electricity system. Now, to keep regulators happy and energy markets fair, we can't just mix these up willy-nilly. We actually have to split the EV battery's capacity into two virtual partitions, one for BTM and one for FTM.
Section 2. 4 streams of value.
Once those virtual partitions are set up, how do we make money? We use an additive stacking approach. Basically, instead of using the battery for just one chore, we layer on 4 distinct applications to build up the financial benefits. Let's start with the behind-the-meter stuff. The first stream is self-consumption increase, or SCI. This is where you use the EV battery to store local renewable energy, like from a company's rooftop solar panels to use later. By aligning when vehicles plug in with when the sun is shining, commercial fleets avoid buying expensive retail electricity. It saves businesses some serious cash.
Our second BTM application is peak shaving, and historically this is a massive moneymaker for commercial setups. See, large commercial consumers aren't just billed for the total energy they use, they get hit with huge financial penalties for peak power demand spikes. If 50 EVs plug in at 9 a.m. all at once, that's a massive simultaneous load. Peak shaving uses the EV batteries to supply power locally to cap those spikes, completely sidestepping those massive fees.
All right, now let's cross over to the front of the meter applications. The third value stream is the frequency containment reserve. The transmission grid has to be constantly stabilized at a very specific frequency. It's kind of like the heartbeat of the grid. In Europe, for example, that heartbeat is exactly 50 Hertz. And guess what? Fast-responding lithium-ion batteries are absolutely perfect for this balancing act. They can discharge or charge in these rapid, short bursts of power to keep the wider grid perfectly stable. Our final front-of-the-meter application is spot market trading. This adds a really dynamic, highly responsive layer of profit. Because EVs can charge and discharge so incredibly fast, fleet operators can actually engage in arbitrage trading on the intraday continuous market. Put simply, they buy electricity from the grid when volatile prices plummet and sell it right back when prices spike. Buy low, sell high.
So let's put this whole puzzle together. First, the EV provides basic mobility. Obviously, that's a given. Second, it serves those consumer-side BTM apps like peak shaving. Third, it serves the grid-side FTM apps like spot trading. But step 4, that is the real secret sauce. The highest level of optimization happens when the system allows front-of-the-meter energy to be virtually shifted to the behind-the-meter partition to be used for driving. Stacking these 4 streams and allowing that cross-partition shift unlocks maximum flexibility and, yeah, maximum profit.
Section 3. The battery life paradox.
Now you might be thinking, and it's a totally fair hesitation, if we're stacking all these applications, aren't we going to absolutely wreck the battery? The intuitive assumption is that excessive charging and discharging for all these grid and building services will just accelerate battery degradation, right? If you work a battery harder across 4 different jobs, it stands to reason it'll die much faster.
Well, get ready because this is wild. It's actually a complete paradox. Look at standard, dumb, unidirectional charging, which is basically just plugging your car in and blasting it to full immediately. That gives the battery an expected end of life of about 7.9 years. But if you use a smart, degradation-aware, bidirectional vehicle-to-grid algorithm, where the battery is actively doing all 4 of those jobs we just talked about, it actually pushes the lifespan to 10.3 years. The battery literally works more, but lives longer. Crazy, right?
So why on earth does this paradox exist? It comes down to stress. A standard plug-in and max-out approach stresses the battery out by holding it at a super high voltage. But a smart optimization system, it actively manages the battery's health. It completely avoids preemptive high-power charging. By trading energy back and forth, it keeps the battery in a healthier, broader state of charge band, meaning its overall percentage, and drastically cuts down the time the cells spend at those stressful high-voltage levels.
Section 4. Scaling the EV fleet.
So what happens when a commercial operator scales this multi-use strategy across an entire corporate fleet? When you add the first 10 to 20 vehicles, you see a rapid spike in revenue per vehicle. The synergies of shared solar generation and optimized demand peaks really drive those profits up. But eventually it flattens out. Once a fleet hits around 100 vehicles or so, the revenue per vehicle saturates, simply because the building's specific power load and solar capacity are fully maxed out by the fleet.
But even with that saturation point, the financial payoff is absolutely staggering. 2,224 euros. That is the peak extra annual cash flow generated per vehicle when a fleet operator flips the switch on all these optimizations, compared to just dumb charging. Multiply that by a fleet of 50 or 100 vehicles, and you are looking at some massive revenue generation from assets that would otherwise literally just be sitting idle.
To sum it all up, treating an EV as a single-use tool is a massive missed opportunity. Taking a Swiss Army knife approach is the absolute key here. Unlocking maximum profit requires stacking all 4 value streams, utilizing bidirectional vehicle-to-grid tech, and crucially, permitting that regulatory energy shift from the front-of-the-meter to the behind-the-meter partition. It's the whole shebang.
I want to leave you with a thought that completely changes how we look at electric mobility. When we pave a lot for a commercial fleet, are we really just building a place to park cars for 96% of their lives? Or, with the right software and bidirectional chargers, are we actually building the agile, decentralized, and highly profitable power plants of the future? Thanks for joining me for this explainer today. I have a feeling you'll never look at a parked EV the same way again.